Okay, thank you very much. So I guess I should put forcing. Thanks for the invitation for this wonderful workshop. So this talk will be based on a few recent and ongoing work. So the first is, of course, the EFThedron with Nima and Zhen, who is a graduating PhD student from Caltech. And then a new recent development that we put out last month. This is along with Li Yuanjiang, He Wen, who are actually undergrad students here at NTU, and Li Wei, who is a master's student going on for PhD, and Laurentio, who actually I think a lot of you know. And of course, there's an upcoming follow-up, which is called the modularhedron, which is actually the second part of this talk. So let's begin. So I'm just going to directly go to the gist of this talk, which is basically this is the object I'm going to be interested in, and that is the convex Hall of the product moment curve. So it's a convex Hall, and so you're summing over positive sums over. So one of these are each one are a moment curve in the sense that it's a curve in a higher dimension space parameterized by moments. But now we actually have a product of them. So this is the mathematical object that I'll be interested in. Now, in practice, these two moments might not be identical. So for example, one of them might be confined to the positive region where x take up positive values, or in some bounded region, or in some cases even discrete. So these are not really symmetric in the practical cases that we're using them. Now, so the goal is to find the boundary of this Hall. So we want to find, so if something is given, if some big matrix is given by the convex Hall of this product, then we like to find the full set of equations that carves out the image of this Hall in the space of Y. Now, actually, this is a well-studied problem in mathematical literature. So in the literature, this is usually called the multivariate moment problem. And it is phrased as, what are the sufficient conditions on this Y matrix such that you guarantee that a solution of this form, this product form, actually exists? So of course, if we have the sufficient condition, then that's basically the boundaries of our Hall. So so this will be the object that we're interested in. So before talking about really go into the boundary, let me just talk about where do this object appear. So we're going to find that in two theory spaces is actually governed by this precise product geometry. One is in the problem of bootstrap problem in 2D CFT, where we talk about the partition function, the torus partition function, and applying modular symmetry. And the other is the effective field theory story, where we talk about Wilson coefficients and we impose symmetry involving permutation or cyclic symmetry. So I like to start by just showing how these two, this object here, I think this is clear enough what it is. So I would like to show how that object appears in both of these stories. So let me just start with the torus partition function. So we talk about when we talk about a two-dimensional CFT, we like to put it on a torus, and then the partition function is going to be written as a sum over the character, which are the contributions of the different Virasoro primaries. Now here, the positive sum is coming from this n here, which is the degeneracy number of each state. So each state is parameterized by h and h bar, which is the left and right moving dimensions. So the conformal dimension is given by h plus h bar, and of course the spin is the absolute value of its difference. Now, of course, this partition function is going to depend on your torus moduli, and therefore all of these characters are functions of your moduli here. So we have this object that is given by a positive sum. Now, we like to consider the expansion of the torus moduli around some, for example, some fixed point. So you can consider, so this is like a Taylor extension, but not precisely. So you see that these expansion operators are engineered such that the coefficients that you get are simple. So for example, if you expand around the S self-dual point, then what you have is the left-hand side, because you can expand both in tau and tau bar. So the left-hand side, you get a matrix. And on the right-hand side, you'll get the expansion coming from the characters. So on the right-hand side, you get that this matrix, this expansion of your partition function is given by the degeneracy number multiplied by the expansion of the characters. There's two characters. One is the holomorphic, the other is the anti-holomorphic part. And therefore, just from the get-go, you have a product geometry. If you look at the expansion coefficient of the characters, you'll see that it comes in very nice compact forms, where this X here are the things that we're interested in, because they actually depend on the Hn and H bar. So and when you have a theory with the spectrum, the information is encoded in the Hn and the values where H and H bar take. So this is essentially just a simple polynomial of H and H bar. The fact that it's a simple polynomial means that you can just take this GL transformation. So let's take a GL transformation. For example, I work out the 3×3 form. You act on this character expansion coefficient. You do a GL rotation and you just get a moment. So that's how the moment appears. So basically the statement is that you take the torus partition function expanded around the self-dual point, subtract the identity part, and then perform a GL rotation. You get exactly the product moment that we just seen. And actually, if you're interested in for example, if you're talking about we're interested in, we're trying to find the gap, the twist gap, and so forth, you just do a further GL transformation, such that and then you still get the same geometry, but the geometry starts from the gap, and therefore you can just apply the whatever constraints we're going to have on this rotated form. So we've seen
at this point you're not caring anymore that the coefficients are integer. Is that right?
Actually, so the statement is that at this, there's two geometries. One is in this H bar basis, where this manifests the unitarity, because both H and H bar are positive. Mm-hmm. Now you can further rotate into the delta J basis, and the delta J basis you can impose discreteness, mm-hmm. where J is a spin. So you can actually have both. So both impose the unitarity constraint.
No, but I mean in your hull, those ends are integer. But when you're
the ends,
geometry, you're not going to care about the fact that the ends are integer.
Yeah. And actually, the ends are strictly not. I mean, the original ends are integer, but because I've done all these rescalings so they're with rescale factors, so they're not supposed to be integer anyway.
No, here they're not. But I'm just saying the obvious thing. There's some extra constraint ultimately when you do the GLs back that the ends are integer. I mean, often integer hulls are a little bit smaller than full real hulls. So, but anyway, you're gonna pretend that the ends are real and positive from now on.
Yeah, right. Yeah, and actually it'll be nice to incorporate it and also if for the EFThedron as well, these partial wave coefficients are bounded from above by unitarity. It'd be nice to impose those as well. But yeah, I'll mention this in the conclusion. Right, and of course, so we have that basically the punchline is that the partition function is living inside of this kind of product geometry, and then we want to slice it through by again a subplane, and the subplane is given by modular invariant. So modular invariant tells us that we change the torus moduli, the partition function should be the same, and that's actually why people usually use this kind of differential operator to define the expansion the expansion coefficients, is because the modular symmetry is then very simple. It's just the n plus n odd components are 0. So this is the form of, so this is saying that the partition function must live on the subplane in the full space. And therefore the entire modular bootstrap is just this. So this picture I'm going to use over and over again because it's the same thing. So you have some convex hull of product geometries that is giving you this space, and then I'm slicing through by this modular plane and looking. And so we're looking we'll be interested in the intersection geometry. Okay, so now we're going to switch to EFT, where we're going to see exactly the same geometry appearing. So this, I guess this is probably a familiar story for many of you. So we basically know that starting from the 4-point amplitude, so we know that the amplitude is bounded near the forward limit when S is large. Therefore, we can write down this kind of a contour integral, where if the contour is encircling infinity, then because the amplitude is bounded, so in general, this infinity will vanish. And therefore, this tells you that there's a relationship between the contribution from the origin, which will be EFT coefficients, because around S equals 0, the theory or the amplitude is governed by the EFT description, which has a polynomial expansion in S, and those polynomial expansions are the EFT coefficients. And this must be related to the residue or the discontinuity of the UV state. So we get this kind of a dispersion relation between the EFT coefficients and the discontinuity. And usually we sit in the forward limit, but in recent years we've learned to appreciate to explore the geometry away from the forward limit. So we'll do a Taylor expansion on T on both sides. And therefore we'll have this kind of dispersion relation where GKQ is the coupling constant of your Wilson coefficient. It's basically related, I guess this form will be more enlightening, which is going to be related to this is the contribution from the residues, and these are the contributions from the discontinuity. And of course, importantly here, unitarity tells you that these expansion parameters are always positive. And so this is the positivity that is playing the same role by the degeneracy number in the modular bootstrap. Now, of course, this has been explored in many work that has been done for the past few years. So I've just listed a representative few of them. So we would like to explore actually what is the convex hull of this space. So if I write down explicitly the GKQ here, so you see that so this is the discontinuity and this is the residue. So you see that it's not much difference. The only difference that you're integrating over a continuous spectrum where this is discrete. For us, continuous or discrete is not really doesn't make a difference. So we're just going to use just the sum for now on. So basically, the statement is that you're summing over all states. The state is contributing with, of course, its mass. And there's some polynomial here, which is related to the Taylor expansion of your Geigenbauer polynomial. So for example, here you already see you have a geometry. So if you organize, the Q expansion is related to the T expansion. So it's related to the expansion of your Geigenbauer polynomial. So you would, if you just organize the Q here into a vector, then you immediately see that you actually have a convex hull. So let's look at this convex hull closely. So first of all, I'm going to make things simple. So here, this formula is actually a little bit complicated. I've hidden a lot of details in here, but here this is coming from contributions. If we go back to the previous, we see that there's contribution from the S channel and contribution from the U channel. You'll see the contribution from the U channel includes T in it. So the contribution from the U channel is going to be slightly more complicated. So I'm just going to focus on the contribution for S channel for a few slides before going to the full geometry. So if I'm just looking at the contribution from the S channel, so I'll put an S here representing this is just S channel contribution. Then the geometry is simple. I have the dependence on M and the dependence on the coefficients of my Geigenbauer polynomial. So for example, if I focus on D equals 4, where this VL is defined as the Taylor expansion of the polynomial around 1, then I just have this simple geometry. I have that these Wilson coefficients are given by the product here, which is the mass moment. And here let's just call it the spin moment here. Now, of course, if you write this out, these VLs out, there's a closed formula, not surprising that there's a closed formula here, but it might look a little bit unenlightening if I write it in this form. But I can, instead of using L, I use the Casimir invariant form where J equals LL plus 1. Then if I write it in J, then it has a very simple form, which is just the product. But the fact that it's just a product with increasing degree in Q tells us immediately that we can just perform a GL transform again on this entire thing. So along the direction of your row, and then this part can just be directly rotated into a moment again. So we see again our geometry that we have here. These are moments, and here this is another moment. So it's just a product moment. Of course, here the J's are going to be discrete. So this is what I talked about before. Sometimes the moment is the one side of the moment is going to be discrete. The other side is going to be continuous. But once again, we have a product moment here. And so we're going to call this since I'm parameterizing this by A. Of course, A is GL rotated related to the real couplings G. So we're going to call this the A geometry for now. And so we see that that once we have the A geometry, once I give all the boundaries of the A geometry, which is just the product moment geometry, I can just GL rotate back to the real physical coupling space. And again, now I can ask for, here we just have S channel. Therefore, we can impose cyclic symmetry. And then I just have this, again, the same picture. So this is the GL rotated image of the A geometry, and then you're just intersecting with the cyclic plane. So this is if you just have the S channel. Now let's have the full thing. So for the full EFThedron, things are more complicated because of the fact that you have both S and U channel contribution. So in light of this, to manifest this kind of S and U symmetry, instead of using S and T, we switch to a new parameter, which is T and Z. And the fact that you have SU symmetry is just reflected in the fact that you only have Z, your EFT coefficients only have Z squared. Even powers in Z. So once again, we use the dispersion relation to get a dispersive representation of G, and this is the thing that I wrote down previously. And here you see the full details. So you have this U vector, and the U vector is a projection of the V vectors, the V vectors we had before. So importantly, that this is just a projection. So in other words, if you already know what the boundaries of your V geometry, if you already know the boundaries of your V geometry, once you carve out the space in your V geometry, then you can just do this projection down, and immediately this projection down gives you the boundary of the U geometry. So therefore, we have so this is the complete picture. We start with the A geometry, which once again is a product geometry with one moment being discrete, the other moment is continuous. We rotate it first in the intermediate step, which is the S channel EFThedron, where you can of course talk about if you have ordering, you talk about the effective field theory here. But then all you need to do is just do a further projection. Then you get the SU EFThedron, which is a full EFThedron. And then when just consider the intersection with, for example, if you put permutation symmetry as your symmetry, then we also have an intersection geometry here. So later on, we'll show direct evidence or to just demonstrate for you that just doing this procedure will give you the entire space. Good. So since now I think I persuaded you that in both cases, we have this kind of product geometry sitting at the core. And therefore, now we're going to turn to focus on what is actually the boundary that is implied by this kind of product geometry. So to start my story simple, I'm just going to start with the single moment, which is probably more well known. So let's say if you have a vector that's given by the convex hull of a single moment. So if we start with, of course, these convex hull are always projective. So even if I have three components, this will be in P2. So we're living in P2 space, which means that when we're plotting out the space, it's more natural to talk about ratios. So this is how the space looks like in terms of ratios. So you can see the three different cases. So this is when all of the x's are positive. This is if it's bounded between 0 and 1. And this is if it's discrete. Now this region here, so let's first focus on this region. Now this region, of course, you can see that it's given by by either y0, y1 to be positive, and of course this determinant being positive gives you this space. If you look at it in more detail, then you see that actually the P2 space is actually carved out by the positivity of the leading principal minors of the Hankel matrix. So Hankel matrix is just a symmetric matrix of these y's. So we will consider always the original, the Hanko that starts with y0 and the shifted Hanko, which shifts everything by 1. So the statement is that that space that we've just seen before is just, you can see that indeed is just given by the positivity of the leading principal minors here. And this intuition generalized to arbitrary dimension, and the boundary is basically given, you just take Kn, the arbitrary, by dimensions, we're talking about where we're referring to how many, to which degree you're expanding your vector to. So you just consider, for example, a fixed dimension, you write down the Hanko and you consider all the shifted Hankos, and you require that their principal minor or their leading principal minors all being positive will carve out this space. So let me now, so with this single moment, I'm going to do two things. So first, I'm going to look at these boundary a little bit closely because this will be useful. And the next, I'm going to rephrase this boundary, how you actually derive this kind of constraints is in a way that it's going to be easy to generalize to product moments. So first, so we claim that these are the constraints, that these are positive. We can just put the Hall into this Hanko matrix and see what these things are given in terms of. So if you just plug the Hall into the Hanko matrix and just take the determinant, there's a closed form. And you can see that indeed that this is positive. This is a sum of positive objects, and this is also positive if your X is positive, which means that we're in the half moment. So now you can ask, when does this actually go to 0? So of course we see, since it's a positive sum, is a sum of positive, definite positive objects, the only way that this can be 0 is because you see here that it's a summing for an m plus 1 times m plus 1 Hanko matrix is summing over m plus 1 subset. So obviously it's when you don't have m plus 1 subsets. It means that when the spectrum in your Hall is finite, then this Hanko matrix is going to vanish. Now you might wonder, why is it that so let's say, for example, if at n we need n plus 1 elements, let's say if we only have n elements in our Hall, then you might wonder, why am I getting two conditions? One is this determinant is 0 and this determinant is also 0. Notice that the shifted Hanko doesn't involve y0. So that means that the shifted Hanko doesn't see, there's one element that the shifted Hanko is not seeing, and that element is the element y1000 is not seen by the shifted Hanko. So for example, you can have the shifted Hanko equals 0, but the original Hanko is not 0. That means that it has at most n elements plus the origin. But just the fact that the vanishing of these Hankos corresponds to the rank of or the number of elements in your Hall, that tells you that the boundary actually has a hierarchy. So for example, you can start with the codimension 1 boundary, which is the largest Hanko, the largest shifted Hanko being 0. And then just going one step down in this boundary complex, this corresponds to the image of your Hall, reducing in the number of rank. So the vanishing, so in other words, when you have a single moment, the vanishing of the Hanko matrix actually has a hierarchy structure. That you know that there's a preferred codimension 1 boundary and then higher dimension boundary as you go down and downwards. So this will be this will play a role in the modularhedron story later on. Now, the other point is, yes.
Hi. So can you explain the shift 1 corresponding, the shift 1 being 0 corresponding to codimension 1, and then the original one is already codimension 2? Did I understand correctly?
What I mean that you can arrange these things, so you can start with the code. So you can start with the codimension 1, which is the shift 1. Then when this is 0, then on top of that you enforce Kn to be 0.
Oh, okay.
Yeah,
okay.
So that's what I mean. You go downwards, and there's a preferred direction to go inside.
But if you set directly, if you set Kn, determinant Kn equals 0, that's also a codimension 1 boundary, right?
Yeah, but there's a preferred sequence to take this.
Okay. I see. Thank you.
Sure. So now I'm going to turn to another, which is actually a much more easier way to see why these positivity conditions come out, and it's actually to notice that the Hanko matrix of Y. So if our Y is given by the positive sum of moments, then the Hankel is nothing more than just taking these xi, which one xi is just this moment vector, and dotted into its transpose. So, for example, if my Hankel matrix is given in this form, then immediately, I mean, this is just simple linear algebra. We know that if we dot it into an arbitrary vector on both sides, this must be positive for arbitrary vector. And from linear algebra, we immediately know then, of course, then the Hankel matrix must be a positive semi-definite matrix, because we dot it into any V is always 0. If the Hankel matrix is given by this convex Hall form. So the fact that now, of course, here I'm just using xi. This is for arbitrary xi. So I have not forced myself into the half moment yet. So xi can be positive or negative. We'll see what happens when xi becomes positive. Now, but before going to that, so this is saying that if the Hall is given by ci times the moment, then this matrix has to be positive. We can ask if this is a sufficient condition, and you can actually see that this would be a sufficient condition. There's a simple way to argue it if you allow yourself to go to infinite dimension. So if you go to infinite dimension limit, then you can consider some arbitrary function which is given by these arbitrary v times x. And we see that the positivity of the Hankel matrix is equivalent to, let's say, the expectation value of fx squared, which is given, which is defined in this form, is positive, because this is just the infinite dimension limit, infinite dimension being infinite number of polynomial degree. And so we can always, so once we know that this is positive, then we can always organize our V such that fx is sharply peaked around some xi. And once this is sharply peaked around some xi, we can make it like sharply peaked like a delta function. Then we will have that a particular ci is given by some positive. So we will have a solution. In other words, we can engineer such that we can always have a solution in the form of a moment problem. In other words, we can solve for ci. So this is a simple way to argue for why that this is a sufficient condition. Now, we can do more. Now, let's say, so this was for arbitrary xi. So let's say if xi is bounded between a and b. So now we can do exactly the same argument. So instead of just the previous just at ci doing this expectation value, we further impose that not only is this positive, we also have the x minus a and b minus x is also positive. And the reason that this is positive, of course, is because you're enforcing x to be between a and b. So this is, of course, this will be positive. And then once you expand it out, then you see that this will actually require that the following matrix be positive semi-definite. Okay, so let's just look at some explicit example for a and b. Let's say if a equals 0 and b equals infinity, which means that you're in the positive region of x. Then you take a equals 0 and b equals infinity, then the leading piece is just x. So then the condition that you get is this x, the expectation value of x times fx squared is to be positive, and that translates to, so this is xi times xi squared. And if you write out in terms of original y matrix, this is exactly the shifted Hankel that we had before. Okay, so we re-derived why the shifted Hankel needs to be positive using this. If we talk about the Hausdorff moment problem, so that would be a is bounded between 0 and 1. So you can do it. So you just set a equals 0 and b equals 1, and then you can again derive the consequence. And the consequence is the extra condition you need to impose is what is called the twisted Hankel, which is the Hankel matrix of the difference of these components. So for most of us, what we're familiar with is actually cyclic polytope. So you can actually see the constraints of cyclic polytope arising from here. So for example, we say that if we're interested in the discrete moment problem, where we want to have x to take out only these discrete values. So basically what we want to do is we'll require that an infinite sequence of these, starting from the first one and then I plus 1, all of the successive one to n, all of these things, that expectation value has to be positive. And this will generate to give you the positivity constraint. And so if I just pick up any one of these, you can see that immediately this is the usual thing that we're familiar with, which is that y I plus 1 has to be positive. So you can generate all the possible positivity condition using this kind of universal language. Good. So of course the single moment is easy. So all of these boundaries are actually known before. So now let's look at the double moment. So for the double moment, now once we've settled things in the single moment language, now for the double moment is straightforward. Even though we say that we have two sets of moments here, but then the natural thing that you will want to do is just organize this into just a single vector. So this is just a single. So you have 1 x tilde x square x tilde x tilde square and so on and so forth. So you just organize this generalized Hankel matrix. And then you just impose this, you just go through the same argument as before. And so the difference is essentially that in the previous thing, we're talking about expectation values of functions, which are single variable. Now it's just you do exactly the same thing and you have expectation value of functions, which are two variable functions. But other than that, the argument is the same. And therefore, you see that, for example, for the full moment, which means that you don't put any constraint on these x's, then the conditions is just that this generalized Hankel matrix is positive semi-definite. And so then I don't need to do anything now. So depend on what you want for your moment. So if they're all just in the positive moment, then you have the generalized Hankel, again, the shifted in x direction and the shifted in x tilde direction Hankels being positive. If you have both bounded moments, then you have that the shift that these gives you that their x's are in the positive region, and then you further need to impose the twisted Hankel. And if any one of the moments are discrete, then you just impose the discrete constraints for your generalized Hankel matrix. So basically,
can I ask a question? So
sure.
that there is in the way we were talking about it, at least for this particular problem, there was the kind of picture where you take the discrete part, which was a cyclic polytope, and you dotted with the walls of the cyclic polytope, and then you applied the Hankel to the corresponding sort of vector that you got from doing that. And how does that list of inequalities compare to this one? Are they the same?
Yeah, So we know that these equalities, so we can derive those equalities from these ones. So, but yeah, of course.
No, I mean, I think the question I'm asking is, what is the minimal presentation of the boundary structure? Yeah.
So I think that we're not entirely clear what is it. We don't have the complete answer to what is the minimal set. So, but for sure, those that we can derive from these.
But are there more of these? I mean, that's why I'm asking, because it looks like it looks like you can get like lots of inequalities here.
Right.
But the ones that we talked about, I'm sure cut out the object. Maybe they might still be redundant a little bit, but that's why I'm asking the sort of direction in which this goes. What you're talking about here is a very nice uniform way of sort of seeing lots of boundaries, probably all the boundaries there are. But I'm asking about the direction of the inclusion, just to see what the real boundaries are.
Right, we don't have an answer to that yet.
For instance, sorry, I mean, I think independent of it being cyclic polytopes, I think we know that in these cases where you have the direct product of maybe it's not independent of being cyclic polytopes, but anyway, that there are some there's a general discussion of these direct product polytopes, and at least in simple cases where each one of the polytopes is simple. There's an argument that the facets of the direct product polytopes are given indeed by this sort of dumb method dotting with the walls of one and of the other. So that would suggest that the procedure that we talked about in our paper is actually minimal, because you find all the walls of one of them and then you apply Hankel to the other.
Okay, so I didn't, so there's some things that yeah, so actually there's let me just mention one thing, and that will say that there's some issues with okay, that there are some evidence that those are not enough. So let me just go back to this. So in our story, we have one is dotted into in terms of just the discrete one, and then we have the moment problem. So let me just go to the continuous moment problem, and you'll see that why these conditions might not be enough. So as we see here, so this is just a single moment, and we say that just the positivity, it's just the non-negative itself should be able to carve out the single moment space. So this will be what we're saying. But actually, you can see that just from this complex story, it's not exactly true. So let's say if we have even just the determinant of a fixed n to be 0, that will imply that all the higher Hankel are all have determinant 0, right? But actually, to be consistent, it actually implies more than the higher ones are the determinant of 0. It actually implies that all the higher one must have the same rank as Kn, which means that there's actually that it can only have not only the determinant 0, but the rank. So if you do compute the characteristic equation, then all of these coefficients all have to vanish all down. So just imposing that the Henkels are 0 actually are not sufficient. So that there's simple boundary conditions where you can just sit at the boundary and you can see that there's actually no solution to the moment problem at that boundary because of this, because it's, even though it's vanishing for all the higher Kn and you're imposing these things to be vanishing, but the rank is actually different. So there's so there is evidence that we know that these vanishing Henkels are not sufficient.
But this seems to be on the continuous side then somehow.
Yeah.
Because I think that statement about direct product polytopes is just the theorem. I mean, that,
it's just independent of what I'm saying. Yeah, but yeah.
Okay, great, thank you.
Sure. Okay, so let me just how much time do I have? Okay, so let me just show you the consequence of this. So first, let me just show you the EFT. So remember, in the EFT, so what is the procedure? The procedure is that we have these A geometry, which is given by the product moment. One is continuous, one is discrete. Once we carve out this A geometry space, we rotate it to the physical coupling in the S space, and then we further project down to the SU EFThedron, and then we can intersect with the permutation plane to see the region. So let's say if we, for example, I'm just labeling out these couplings so you can see which operator it corresponds to. So the relevant boundaries for the A geometry, well, I'm just listing a few the relevant ones. So here, these are associated with the twisted couplings, which means that you normalize your mass gap to 1. These are so for example, this is a generalized Hankel determinant, and these are the product determinants. Of course, you have infinite number of them, but it turns out in the vicinity of these constraints, only this is relevant. So you carve out the space in A, so in the A geometry. So this is just was a sequence of implementing different subsets of these boundaries. So you have two differences. The only difference is just the additional implementation of the largest generalized Hankel. So this is a space carved out in the A geometry. I rotate, project, and then I get, after the projection, you get the G geometry. Looks like that's this finite space. Now you see that this red region is in this paper by Simone and his collaborator, they use SDP to compute semi-definite programming. So you can put this as a usual bootstrap problem and just carve out the space using semi-definite programming. So the red along with, so this is identical. with their results. So you see that we're nicely carving out this space. There's a mismatch here in this tiny region, which might seem like there's something wrong, that our geometry is not the complete geometry. But remember, as I just mentioned before, that near the boundary, there's actually some consistency conditions that you need to further impose. So for example, we've just imposed a geometry for k equal up to 4. You can ask for each of these points, does it involve a UV completion that completes to k equals 5? Is all points at k equals 4 UV completable to k equals 5? And it says that there exists k equals 5 couplings such that all of the constraints can be satisfied. So if you ask that, so that means that you need to add these conditions in your A geometry for the k equals 5 condition. So all of these involve k equals 5 couplings now. And you need to find, once you have the 4 and the 3, k equals 3 and 4 couplings, now you're asking if there exists a set of k equals 5 coupling such that all of these things are positive. And so then we can hone into this region here, and immediately you see that it starts to rule out this extra region. But because we're doing grid plot, so we're just numerically searching for solutions. So this is the STP and semi-definite programming result. And this is so we've seen that now, indeed, using this geometry, we can now throw away this piece as well.
You just said these words, but just to clarify, you're just going to the higher dimensional I mean, in principle, you don't need to talk about the lower geometry. In principle, you have the whole higher dimensional one, and then everything we get for lower dimensions just by projecting that guy. And so
exactly.
you're just saying that obviously what you get just from the truncated problem is always going to sit a little bit, is going to sit a little bit outside what you get from the full projection. Right. Just like similar, anyway, this is obvious, but we also saw this in the CFT story. I mean, that this is a canonical part of this kind of story. Yeah.
Right. Okay, so this shows you that indeed just giving out these boundaries, you can just directly carve out the space. So now let me just talk a little bit about known EFTs and how they appear in this space. So for example, we can, so again in the same space, so we can, for example, let's just look at the case where you can have ordering. We can consider these various EFTs where you have either the linear sigma model, the massive box, or the string amplitude for bi-joint scalar, and just ask where these things sit in your geometry. So for example, just collecting in a subspace here where I'm now sitting only in the k equals 5, you see that all of these known EFTs are actually sitting at a very tiny corner. So this is actually, we're really zooming into this geometry and looking at where the known theory sits. And you can actually see exactly the same thing if you actually now impose, so switching to, actually all of the story I said before also has similar applications here when you have external spinning states where instead of just scalars, you have photons and gravitons. And so for example, this is the EFT space for the D8 after the 4 operator and D8R to the 4 operator. And when you look at the explicit string theory solutions, they're actually sitting at the tiny, at the tiny boundary here. Okay, so they're actually sitting at a tiny boundary here. So one might ask, why are so very nice, we can have these inequalities that carves out the space. So why is it that the known EFTs are isolated in a corner, in a very tiny corner in the EFThedron? And the reason is, of course, the things that we've imposed so far is actually very weak. All we've imposing is that the dispersion relation and that this is positive. But we know that this is positive is extremely weak. There's actually more constraint on this. For example, let's just take a known EFT, and so for example, let's just take the massive scalar box. We can compute its discontinuity and then expand the discontinuity on the Legendre polynomial basis, and then extract its coefficient. So the coefficient, which is the square of this f function, and then we plot it against spin, you'll see that not only is this coefficient positive, but then more importantly, it actually exponentially decays to zero very fast. So you see that there's a large spin suppression here. And in fact, you see for any known UV completions of effective field theory, you always see this large spin suppression. So for example, this is string theory. You just compute its residue expanded on the polynomial basis, and you see that for each level, it's always that the spin 0 is dominant. So we like to ask, can we actually see this kind of spin suppression emerge just from the geometry of the EFThedron alone? Of course, if we can actually observe this from the geometry, this in itself will not explain why those things are in the corner, because we're using the geometry and we already use all of our constraints on it, and it still carves out that space. But just in the sense that there is some part of the geometry that actually also telling you that the spin must be suppressed. And furthermore, does this geometry actually impose constraints? So usually when we think about this, is we're thinking about these are the UV unitarity constraints imposing on the IR couplings. But now we're in the IR, we're actually enforcing these symmetries, and then we can now in turn ask, is this actually imposing constraints on the UV spectrum itself? And the motivation, of course, is in the CFD bootstrap, where in the bootstrap, you're actually gaining information about gap, about OPE coefficients. And so similarly here, can you start to get information about the spectrum, the massive spectrum in your UV? And the answer is, of course, yes, since I'm asking it, and to see that how this can happen. So the important point of course, is what is the extra condition that comes from the IR? And the extra condition is that the dispersion relation itself does not manifest cyclic symmetry or permutation invariance. And therefore, it is the permutation invariance in the IR that is encoded in a geometry that can in turn impose constraint on the UV. And so just to show you a simple example, so let's look at the k=8 constraint. So k=8 permutation invariance tells us that these couplings has to sum to 0. Now, of course, each of these couplings has a dispersion relation representations for it. So we can just plug in the dispersion relation representation. And in the end, we'll get a function that looks like this form. So it's a positive sum of so this is a function of L. And the point is that this has to be 0. And so by looking at this function itself, then we can see that in the position of this root will actually impose non-trivial constraint on the spectrum. So for example, just for k=4, this is the form of the polynomial. And since our spin is discrete, you can just plug in the spin and you immediately see that only for spin 2 is this thing negative. Anything beyond spin 2 is all positive. So by looking at this, you immediately see that spin 2 must be this part of your spectrum. So you can go furthermore to the next k=7 constraint. So you can organize these things together. And now you can do the sign pattern of this polynomial now becomes everything above spin 4 is positive and only spin 4 is negative. So now you see that spin 4 must also be part of your spectrum. So you can go order by.
How does this work with a simple like tree level field theory that doesn't have any massive spin 2 or spin 4 particles?
Right. So of course, for spin 0 is just 0. So if you only have scalar, then it's of course permutation by itself. So this doesn't. So it's only when you have a higher spin state.
Oh, okay.
Then
I got it. Oh,
yeah,
sorry. Okay.
So when you have a higher spin, yeah.
Okay.
Of course, we know that when you have higher spin, then you need to have infinite. But this is more. This is telling that you have infinite. The spin is unbounded, but these spins must be there. So that's really yeah. Right, so you can just organize this, and so for example, you can show that anything below spin 28 must be present. You cannot. So as you push this beyond 28, now it becomes complicated. The reason is just a very technical issue. Is just that now the things that have negative, actually, there's more than 2 spins having negative when you go beyond. So now you have to look at but yeah. But actually, this spin pattern actually tells you more than just that. It actually tells you that the spectrum, this the spinning spectrum, the spinning spectral function is also bounded. So we can define this average spinning spectral function, which is anything with spin L. So we average with its mass, and so we can define this average as spinning spectral function. And so the original constraint where this sums to 0 now becomes a very simple formula, where pKl times this has to be 0. So previously, for example, if you have, this is probably not a good one to use, but let's say if you have, so if this function WL sits here, then you see that everything is negative. The only negatives is for spin 2 and spin 3, and everything beyond is positive. So let's say if you only have the spin 2 state here, that immediately means that the ratio between any spin here against the spin 2 has to be bounded, because this is whatever is the spectral function for your spin 2, that's the only negative that is given you. And so anything here that has positive, it cannot be too positive. It is bounded by the negative of the spin 2 here. So that means that you can get these spectral bounds. So for example, at k equals 4, you can get for any spin L bigger or equal to 4 relative to spin 2, you get this kind of inverse polynomial bounds. And this is just from that simple minus sign there. And of course, because this is a polynomial bound, you can see that these things are so as you increase in k order, they're more and more heavily suppressed as you go to higher and higher spin for this ratio bound. This line here is this line here is the ratio for the STU amplitude. So the reason that we're introducing this STU amplitude as a benchmark is because this amplitude is appearing at the boundary of many of these plots. And this amplitude, of course, we don't expect it to be a physical amplitude because they have infinite number of particles at the threshold, but it satisfies all the conditions that we asked, that it has positive expansion and everything. So this is the benchmark. And so, of course, this satisfies our bound. Yeah, this is just saying that you can do the same thing if the external states are massless, and then you have the spinning polynomials, and you can do exactly the same thing. And then, for example, if you couple the external state being photon, you can see that for photons, you must have a spin 2, and for graviton, you must have a spin 4 for the massive state starting. And you can do similar analysis there, and also similar spin bound analysis. Of course, now because the S and U channel the S and U channel expansion are different, and therefore you have different bounds for S and U channel. Okay, so I'm going to just mention since I guess I'm running out of time, so I'm going to mention very few things about the modular hedron story. So, but the story is the same. So again, you have this, that the partition function is bounded by the convex hull of this product moment. And then we can ask about its intersection with some symmetry plane, which will be the modular plane. Now I'm just going to talk about the single moment limits because these are more connected to the well-known bootstrap problems. So for example, here, so once again, it's a product. So for example, I can just fix fix one of these moments. So for example, let me just fix to be h bar to the first order and just look at the single moment. So I will be bounding things involving just h. And so this will be what is known as the twist gap bootstrap, because if we just have h and you bound the gap for h, then that's bounding the twist gap. And so if we look at the twist, so if we just have a single h, so once again, you just do a GL rotation to introduce the gap. And then you can, then the condition is very simple, that you have this, that you have the geometry associated with this convex hull. And you require that it must satisfy all of these determinant Hankel matrix to be positive. So now comes the important about this hierarchical complex. So let's stick with let's say we expand to, so it's always nicer to go to odd dimensions. So d equals 2n plus 1. So you can see that the modular plane, or the symmetry that is imposed by modular symmetry, is n plus 1 dimensional. There is a unique and of course, I'm also doing this GL rotation involving the gap. So the total degrees of freedom is the degree of freedom of my modular plane, which is n plus 1, and the gap, so it's n plus 2. So the statement is that there's a unique n plus 2 codimension n plus 2 boundary that sits at the bottom of this complex. And So by imposing the m+2 zeros along this complex, you can actually identify an m+2 boundary, which corresponds to the vanishing of the Hankel matrix above. And this will fix you to a point in the space. So in this space, it's going to fix you with some particular value of the gap, and some, for example, and some particular value for these the central charge. And we've verified that again, using SDP, we verified that for the gap, it matches exactly with the gap extremmost solution in the SDP problem. So since this is carving out the space, so these are giving you all the vertices of that intersection geometry. So we see that imposing this the sequence, we find the gap as well. We also find the minimal value. So you can for H gap, you get the extremal value of the gap. For Z, you get the extremal value of the partition function at the self-dual point. And so you can get this information by doing this this analysis. You can also, instead of this H and H bar basis, you can also consider the delta J basis. So you can consider a linear transformation. Now it's just a moment of the delta basis. So previously it was the twist gap bootstrap. Now, if you consider the geometry of this with only deltas, then this is what is usually called a spinless modular bootstrap problem, and this is the geometry associated with that. And it's just the same thing as I discussed before. You go through this hierarchy of higher codimension boundaries, and you can immediately find the value of the gap for the conformal dimension at that derivative order, and it matches with SDP, with the numerical programming. Okay, I think that's, and this is, I'm just saying that there's actually, so you see that the same geometry between the two problems, and so there's actually a match, a map between the different things that you're bounding. So for example, in the EFT, you're bounding the couplings, and the CFT, you're bounding the partition function, the value of the partition function around some points. And so so we can give bounds for the spectral function, which is going to be similar to the bounds on the degeneracy number in the CFT problem. This is kind of interesting. So in the CFT, we usually have a vacuum. So this is a vacuum that is anchoring your geometry. And actually in the EFT, we also have, and that is the M gap, the gap. So we can introduce, let's say if you know the UV theory starts at some gap, so we can introduce that. And that will be the fixed vector in our geometry. And so in the EFT and the CFT, we usually bound things like the twist gap or the conformal dimension gap. And that will suggest, which is something that we're looking at, is that there's also some gaps. So let's say if your EFT has a UV cutoff starting at some M gap here. And depending on the UV completion, the spin content of your UV completion, what is the next state that must come in after that first state? So is it, yeah, so there's also another notion of the M prime gap, which is the gap above the gap. And what is the highest you can push that state, and what does the geometry tell us? So there should be a similar story here that we're also exploring. So this is the end of the talk. So we see that the convex Hall product moment is basically the linchpin of the geometry behind the modular and the EFT bootstrap. And we see how the intersection of the symmetry plane imposes constraints on the spectrum, and how the geometry imposes the constraint on the low energy, either the low energy dynamics or which I didn't talk much, also on the values of these partition functions. Now I'd like to mention that generalizing to massive external states is actually very trivial. So in the massive external states, basically what you have is once again you have dispersion relation that looks like this. But this just tells you that that it's more reasonable to define your EFT couplings in this kind of linear, this kind of expansion. So S-4m² expansion. If you define your EFT couplings in this expansion, then the EFT couplings will again given by exactly the same geometry. So there's really nothing. It's exactly the same geometry, and it's just that now it's imposing on another GL rotation when you have massive states. So generalization to massive, and of course we can talk about more than just all the mass identical. You can talk about two of them massive, two massless, and do the similar discussion there. Now, as Nima mentioned, and also which is also here in the EFThedron, which is that the spectral parameter has a natural upper bound from unitarity alone. So in proper units, this is P is smaller than 2. And just like the spectral, the degeneracy number, this is naturally integer. So it'll be nice if we can actually also include this information in the, just encode this in the geometry as well when we're doing this discussion. Okay, so that's the end of my talk. Thank you very much.
Thank you, Yatin. Let's thank Yatin for his talk. Or their actions here. Yes. Are there any questions? So I have a question. So there are other methods to approach conformal bootstrap, like numerical bootstrap, as you already mentioned, and then there's like analytic bootstrap. Are some of these methods? I mean, can you understand something from the other methods also in this context? For example, for analytic bootstrap, this is for more than 2 dimensions, but you can consider large spin expansion where the theory behaves much nicer. For example, is there a meaning in this geometric approach to like the limit around large spin?
So that, of course, there's a direct relation between the bootstrap the discussion that we have here so the very first version of the bootstrap where they're doing the derivative expansion at the self-dual point. So these are actually the same. So the only difference is that instead of asking the computer to search functionals to find bounds, here we're just directly looking at the geometry and looking at the intersectant geometry and looking at the vertices. And we're saying that those, so actually the mystery here is actually that why is it that the hand waving, I can say that the vertices, I would expect that to maximize some direction in my geometry. So why is it that it's always the case that the vertices are maximizing in exactly the right direction that the bootstrap problem is trying to maximize. In other words, so we just, from the intersection problem point of view, we just have some plane intersecting some geometry. There's no preferred direction per se in the beginning, but somehow these vertices are exactly maximizing the direction, for example, the direction along the gap, as well as the direction along the self-dual point of the partition function at the self-dual point. These two values, they're maximizing exactly matches with the STP. So it'll be nice, for us, we'll try to understand why is it that that these things line up. Why is it that it seems to be the case that always these vertices, one of these vertices are exactly maximizing in the correct direction. In other words, it could have been that you have 2 vertices and then the boundary is somehow curly and the maximization is actually not at the vertex, but at some curly intersection that is maximized. But it seems that it's never the case. So there must be a geometric explanation for that. For the other, where you're actually you're taking the bootstrap equations to different limits, because we're actually fixing at the self-dual point. So this doesn't have relation to those limits, but probably what the correct thing to say is that then it'll be interesting to look also just analytically at the geometry and those limits as well, is what I would probably say.
I think Yutin, maybe an aspect of Tomek's question, which is, I think, still an open question in this for higher dimensional CFTs, is what is, here at 0th order, what's going on is that moment curve, cyclic polytope, the most basic sort of positivity, shows up because we have orderings. We have an ordering in spin, we have an ordering in dimension, and so we have at least in the EFT story, at least, or in the modular story, it's just ordering in dimension. You just have H and H bar. In the EFT story, we have ordering in spin and ordering in dimension. But for general, going back to CFTs, for general CFTs, I don't think we know what the geometry of general conformal blocks is. We know what the sort of geometry of the SL2R blocks are, the simplest blocks, because all we have is dimension. So there's naturally an ordering in dimension, and it's a standard kind of positivity that you're talking about. But once we have dimension and spin, it's not clear how to think about we don't understand what the geometry is associated with conformal blocks. Whether you expand around the self-dual point, however you think about it, we don't, at least I don't have a picture yet for what the geometry of conformal blocks looks like. And I think that seems to be like the central thing to sort of try to understand better.
Yeah, and we're actually getting away from that by the fact that this is actually a product. So as you go to higher dimensions, it's no longer just a simple product.
Right.
And so we're able to get away from that because this is just a, yeah, it's just a product. So you can still stay within the ordering in individual products. But yeah, and once we go beyond 2 dimensions, it's no longer a product.
But you know, it could be that somehow an expansion. I mean, I don't think. Well, I certainly never looked at this. I don't think I don't remember talking about this with you or Huang either, Tim. Maybe something nice happens, like manifestly when you expand around large spin. Maybe something simplifies in the structure of the geometry as well. I don't know. I mean, whether there's naturally an expansion of the blocks in powers of 1/spin. And whether that expansion shows some more simple geometry.
I mean, for sure, there is an expansion for.
No, I know that there's an expansion, but whether the expansion has any nice makes the geometry of the blocks more manifest. That's the question.
Any more questions for you, team?
You can actually. I had a very quick question for you. So if we look at where you end up in the EFThedron for realistic theories, I thought that even after imposing the permutation plane, symmetry plane constraints, which greatly reduced the size of the space, of course, even then we were closer. I mean, even then we're not in the middle of the space somewhere, but we're still close to like boundaries. Is that correct? I mean, what you're saying with these constraints on the higher spins and so on are sort of consequences of just being on the symmetry plane, right?
Exactly.
So it's not fully explaining the low spin dominance. In other words, low spin dominance is even more dramatic than that, which is already very interesting that you have these big constraints. But low spin dominance is somehow it looks more exponential rather than power somehow. Yes. Is that the point?
Yeah. Well, of course, the usual proof I mean, there's a usual proof that it must be exponentially suppressed at large spins. Of course, here our bounds are not exponential, it's polynomial suppressed, but of course it's valid at finite spin as well. But the real thing is really much more dramatic than, as you say, we're using just the geometry itself, so it's still within that space.
But if I just say it again, if we didn't know anything about permutation variance, we have these sort of big regions. We put crossing, and then now we have these quite small finite regions, and your inequalities are sort of characterizing that much smaller region. But on top of that, we're still closer to some of the low spin vertices of that region. And in realistic examples, for example, you have these like the PL over P2 went like 1/L squared or something like that, if I remember properly.
Right.
But in the actual examples, it's going like something more exponential in L. So that's still the thing to be understood.
There's one small aspect. One small indication, which is that. Let me just go to this. Yeah. So this plot here. So of course, yes, it's always polynomial bounded, but because it's really, I mean, so it's really this. What's happening is just that the same PLI is you're using the same PLI for each of these. And as you go to higher and higher K, they're actually starting to get more and more suppressed. So maybe it's that you need all of them to be true for a fixed PLI, and then and then this.
I think as we talked about at some point, that there's a simple limit. I think it's your K. As K goes to infinity, it's manifest that this is exponentially small in L. Because as K goes to infinity, these moment curves become these averages. The PKs become totally dominated near threshold, near the threshold of the branch cut. And then because we know there's the velocity suppression near threshold that's exponential, the classic barrier penetration associated with the angular momentum barrier, we know that at large K, this must go exponentially with L, and we can even, I think, compute what it looks like with L, because it's just the angular momentum barrier problem. Actually, it would be interesting to see if this the 1/STU amplitude. What does the 1/STU amplitude look like in that limit? Perhaps one can. Well, I guess we see it in your examples, because you're saying that we're getting something. I guess from your polynomials, we actually see that already, because we see that as K goes to infinity, it dies faster than a power of L for any K. So I guess from your expression, we would also predict that at large K, it's exponentially small in L.
Yeah.
Okay, thanks.